Welcome everybody for the Rocky Mountain Mathematical Physics Seminar. Today we have a speaker, David Aasen from Microsoft Station Q in Santa Barbara, California. And he will speak about characterization and classification of fermionic symmetric enriched phases. Thank you, please.
Okay. Oh. All right, we're good? Great. Okay, yeah, thank you so much for inviting me here to give this talk. It's a great pleasure, and I really enjoyed all the discussions I've had since being here. So today I'm going to talk about sort of a large body of work that I worked on during my postdoc at Microsoft and also KITP about characterizing and classifying fermionic phases in the presence of symmetry. And we'll see that this is like a really big extension problem where the complexity kind of grows as we follow these arrows along. And I'll hopefully be able to convey some of the sort of physical aspects of this as I go through the talk. And I won't be able to give a complete summary of everything. Some stuff will be brushed under the rug, but hopefully it will serve as a nice overview of the work. Okay, and the outline is to start with a sort of general discussion of gap phases of matter, how we describe them in terms of modular tensor categories when we're looking at 2 dimensions, and then the fermionic version.
Could you share the slides?
Yeah, that might be hard for me if I want to do that and also be able to see my slides. Share screen, desktop. Is that okay?
That's wonderful, yeah.
Perfect, okay. Yeah, so this is basically the outline. I'll start by some general comments on gap phases of matter, how we describe them in terms of modular tensor categories, and then the fermionic version of this, while mentioning some caveats. And then I'll discuss how we introduce symmetries into these systems and how we think about sort of symmetry enriched fermionic topological order. And I certainly could not have done this without my collaborators, Parsifal Anderson and Christina Knapp. And everything I say is based on these 2 works. The torsorial actions on G-cross braided tensor categories is sort of the mathematical workhorse that we made use of. And the physics results are all contained in the first reference, which will compose most of the talk. Okay, so first, just some broad introduction about gap phases. So we're going to focus on 2 spatial dimensions today. So in the top right, you see a torus, and we imagine there's some microscopic lattice sitting inside there. And we have a Hamiltonian, which is a Hermitian operator that acts on a Hilbert space, which in this case is the tensor product over local Hilbert spaces. And when I say local Hilbert spaces, I mean, it's just some finite dimensional Hilbert space that we associate to the, say, vertices of that graph shown in the upper right of the screen. And then we require our Hamiltonian is also a sum of local terms, meaning that they are supported locally on that lattice. All right, now this Hamiltonian may have many parameters and a complicated phase space. Now today we're going to be interested in gap Hamiltonians, meaning that if we look at a very large system, we should find that the spectrum, so if you look at the eigenvalue spectrum of the Hamiltonian, should look something like this. There'll be a ground state, or maybe a few ground states, and then a large gap to all other excited states. All right, and there's some technical subtleties in defining that, which I don't want to get into. All right, and then the excitations that we'll be thinking about will be sort of localized lumps of energy that sit inside this lattice, and we'll describe localized lumps of energy that carry emergent topological degrees of freedom, which we will identify with the degrees of freedom in a topological quantum field theory. So the low energy degrees of freedom of these Hamiltonians that we're considering will be described by a TQFT. Okay, so in the absence of symmetry, there is a belief that all gap phases in 2+1 dimensions are fully characterized by topological order. And what I mean by this is, is basically we can think about all the universal quantities, topological quantities that we care about for this gap phase in terms of a unitary modular tensor category. That will be the thing that that's sort of an invariant of a gapped phase of matter in 2+1 dimensions. And we'll say that two Hamiltonians, points in parameter space, realize the same phase if they can be continuously deformed into one another without closing the gap. All right, and there's two sort of major subtleties that we'll address today. One is that if our microscopic degrees of freedom are actually fermionic, which in this case will mean that our local Hilbert spaces are supervector spaces. This notation means we have p even vectors and q odd vectors. And this is in contrast to what's conventionally done, where you just consider sort of local bosonic Hilbert spaces. And one of the main subtleties that we'll have to address is how these supervector spaces sit inside our effective description of this gap phase of matter. The other subtlety that we'll have to think about is how we introduce symmetries into these systems. And of course, these symmetries will have to interplay nicely with those fermionic degrees of freedom. And so what one finds when you introduce symmetries is, well, first off, not all Hamiltonians are symmetric, so it will cut down on parameter space. And moreover, certain Hamiltonians which realize a topological order may realize, may have the symmetry act on them in different ways. So it provides sort of a finer grained classification on the set of gap phases. All right, are there any questions at this point? Feel free to interrupt at any point as well. Okay, so let me just touch on some of the previous work in classifying symmetric fermionic phases. So this is actually a pretty old subject by now. It's been going on for 7-8 years. And there have been many ways of tackling it. So one is the so-called defect decoration, which amounts to building explicit Hamiltonians whose microscopic degrees of freedom are truly fermionic and fluctuating over the degrees of freedom in a coherent way, such that the whole system is symmetric under some group. All right, the other, another widely used technique is classifying fermion SPTs using spin Vortism. This has been pioneered by people like Dan Fried, Anton Kapustin, and others, which is a very powerful tool, but doesn't necessarily give you a lot of physical intuition for the systems. You know, in this defect decoration, you actually see the microscopic degrees of freedom and explicitly what's going on there. The last way is this sort of G-graded fusion categories, which is in some sense a fancy way of building these defect decorations. So the G-graded fusion category can be used as an input for building a defect decoration. So all three of these sort of characterizations of fermion SPTs can be related, and we'll see how they sit into the classification that I discussed later. Today, we're going to be taking a different approach. We won't build microscopic Hamiltonians. We won't talk about spin Vortism. What we'll talk about is more similar to what's on the right side of the screen. We'll be looking at sort of the algebraic properties of a fermionic topological order in the presence of symmetry. Okay, so in particular, we will also look at the invertible phases, but we'll also look at non-invertible phases as well. And so in particular, these sort of works here are all looking at fermionic phases of matter, which only have one kind of non-trivial excitation. The kinds of topological orders we'll look at today will actually have many different kinds of topological excitations. All right, and in 2020, there's actually lots of work in this field. So in particular, Mason Barkeshli's group put out 4 papers, and then there's this other paper by Ningji, Gu, and Wang. They all discuss various aspects of this problem. So in those first 2 papers, they looked at symmetric invertible fermionic phases, again using a diagrammatic calculus. In these next 2 papers, they looked at how the symmetry, is fractionalized in these systems, which I'll touch on in just a little bit. And in the last paper, how the symmetry is fractalized and the anomalies that appear. And in this last paper, they just looked at the anomalies. So all three of these pictures will sit in this talk in some way, and I'll highlight that as we go along. And we also build the sort of full algebraic G-crossed braided tensor category theory for fermionic phases. All right, so here's the outline. I will start by discussing a little more about modular tensor categories and then their fermionic relatives, and then all of these symmetry extensions that I mentioned. Okay, so in the bosonic setting, we believe that topological order is described by a modular tensor category. And for us today, a modular tensor category is just going to be a list of data. And I will list that data out and explain how we interpret it in the physical system. So first off, an anion is a topological excitation sitting inside a 2D material. You can have analogs in higher dimensions, but today we're just going to be talking about 2 dimensions. And they carry labels, which are meant to represent local excitations, which cannot be made locally. Okay, anything that can be made locally we'll call a trivial excitation. And so typically we just pick out one label that represents that whole super selection sector, and that's what's identified with the simple objects in the modular tensor category. And here's a list of what those might look like. So A, B, C, and so on. All right. Now, the next thing we can do to our system is take 2 of these super selection sectors and push them together. And this should, again, appear like an anion in our system. Okay, and if you want to think about a space-time picture which represents this process, it would look like so. So here is sort of world lines of the particles or simple objects A and B, which move closer and closer together and eventually fuse to C. This index mu is meant to represent the number of distinct ways in which A and B can fuse to C. And so there's some Hilbert space that we can assign to trivalent pictures that look like this, which represent sort of the number of distinct ways that we can fuse anions together. Similarly, there will be dual vector spaces, which describe how anions can split in space-time. Okay, and yeah, any sort of wave function that we want to write down can be built out of sort of trivalent junctions that look like this. All right, any questions at this point? Okay. All right, so the next piece of data to consider is the F symbol. So if we look at the top left, we have a vector space whose external labels are A, B, C, and D. Via those trivalent junctions, we see that we can decompose it in 2 distinct ways. And those 2 distinct ways should give good bases for that vector space. So on the left side, we've decomposed the fusion space of A, B, C, and D through this channel X. And on the right side, we've decomposed the fusion space A, B, C, D through the channel Y. If we take the direct sum over X and Y, we find isomorphic vector spaces. So they should be related by unitary transformation. And that unitary transformation is called the F symbol, as shown here. Now, we can't make arbitrary choices of F symbols. There's a constraint on them, which is known as the pentagon equation. And the pentagon equation is sort of 2 distinct paths of fusion trees that both start and end at the same place, but arrive in distinct ways. All right, so next, we can have 2 anions in the plane and move them around one another. That's called braiding. The space-time picture will look like this one on the left. So we have C for splitting into A and B, and then we've braided B with A. And so those 2 pictures live in the same vector space, so they should be linearly related. And the linear relation between them is the so-called R symbol. Okay, and the R symbol, just like the F symbol, is also subject to a consistency condition, which is called the hexagon equation. All right. Okay, so now let's move towards fermionic topological phases. And I first wanted to describe that there are two distinct ways that people think about fermionic phases, at least in this sort of algebraic setting. One is to take a bosonic theory, so just a vanilla modular tensor category with a fermion in it and interpret that fermion as a physical fermion, or some people say as a local fermion. The other way which people attempt to think about fermionic phases is to take a bosonic theory enriched in supervector spaces and spin structures. And so this might be called a superpivotal braided modular tensor category. And those will be two distinct ways of thinking about how this supervector space embeds in our TQFT description of our gapped fermionic phase. So the second approach has not been explored in the literature, although I hope someone does someday. I think it would be very exciting and perhaps alleviate many of the confusions that we've had about fermionic phases in recent years. The approach I'll take today is more phenomenological because we are really just interpreting emergent fermion as a physical fermion in a modular tensor category, but it does drastically simplify the problem. Okay, any questions? Everything is crystal clear. Great. Okay, so now let's move into fermionic modular tensor categories. And I'll use M to represent modular tensor categories that have a fermion that we're interpreting as a physical fermion. All right, so this M has an object psi, which is the fermion. What does that mean? Well, for us, so there are multiple kinds of fermions that you could have, but the simplest possible one that you could consider is the following. So it has Z2 fusion rules, meaning if I take a pair of psis and fuse them together, this locally looks like the vacuum. And it also has this -1 statistic. So if I braid psi with itself, I'll pick up a minus sign. Because it has Z2 fusion rules and this -1 statistic, this means that every object in our modular tensor category comes with a Z2 grading determined by the full braid with this fermion. So if I perform this full braid, every object will either pick up a minus sign or a plus sign. And in physics, we have names for those. The objects which braid trivially with the fermion, so the plus sign, we'll call quasi-particles. And the objects that braid non-trivially with the fermion we'll call vortices. Okay, so the Z2 grading allows us to rewrite M as the direct sum of two categories. M0 is a subcategory of M, and you can view M1 as a module over M0 if you like. So the objects in M0 we'll call quasi-particles, and they're described by what's called a supermodular tensor category. And the objects in M1 are called vortices. So a nice result, which was, I guess, proven in 2016, is that if you have one modular extension of M0, then you can always find 16 distinct modular extensions. And so when we do our classification, this will be one piece of data that has to sit inside our whole classification table at the end of the day. So watch out for that. Oh, did I skip something? Okay. The other thing we might consider doing is classifying G-symmetric fermionic phases with respect to a fixed supermodular tensor category or with respect to a fixed fermionic modular tensor category. These are sort of just two different perspectives of the same classification. And at some point, sort of towards the end of the talk, I'll focus on this one. Yeah.
So if I have a UMTC of a fermion, I'm guaranteed to have like an equal number of quasi-particles and vortices.
You're not necessarily guaranteed an equal number, but they will have the same total dimension. So the sum of quantum dimensions squared in the quasi-particle sector is equal to the sum of quantum dimensions squared in the vortex sector. And we'll see an example of this in a moment. Any other questions?
This 16 probably corresponds to stacking P plus IP.
Exactly that. Mm-hmm. Any other questions? Okay. Okay, so I wanted to give a list of examples. These are called the invertible fermionic orders. and they're called invertible fermionic phases for a somewhat technical reason. If you place them on any closed manifold and condense the fermion, you'll always find a unique ground state. As a bosonic theory, these would be non-invertible. Okay, so what are these theories? Well, the quasi-particle sector M0 is always just the trivial object and the fermion. And then one finds that there are 16 different ways to add vortices to the system. And those 16 distinct ways are labeled by a number that lives in Z16 called the central charge, which tells you something about the boundary modes of the system. Or you can think about it as telling you what the topological spin of the vortices are. So you can see that it's related to the parameter nu on the right side of the screen. And the definition of the topological spin is on the top right. Sorry. A sub 1, so the 1 means it lives in the vortex sector, and A just means it's one of the objects in the vortex sector. So I'll show what the vortex sector is right now. So the vortex sector sort of takes two forms. If nu is odd, you only have one object, sigma, and it has quantum dimension √2. If nu is even, depending on whether it's 0 mod 4 or 2 mod 4, the fusion ring of our theory will either be Z2 times Z2 or Z4. Okay, and all of the topological data in these theories can be parameterized by this integer nu that labels the theories. Okay. All right, so this is related to a comment that Mike made, which is actually more general. So there is an operation that you can do on fermionic phases called stacking, which physically just means we take two systems, we place them on top of one another. They both have a physical fermion in them. So we identify the physical fermion of the first system with the physical fermion of the second system. Mathematically, what this means is we add morphisms to our category. So it starts as just a direct product of k nu and k nu prime, for example. And then we add morphisms to our category, which identify psi psi with the vacuum. And what that identification does is forces the fermion in the first layer to be isomorphic to the fermion in the second layer. And this is a procedure called anion condensation. And I apologize for not putting any references. Thought I had them at some point, but it's a well-established technique in the literature. Okay, so in particular, condensing psi psi will pair quasi-particles of the first layer with quasi-particles of the second layer, and it will pair vortices of the first layer with vortices of the second layer. Those are sort of the objects that are left over after the condensation process. All right, now, with the way I've described it, it should be intuitive that the operation is commutative. It doesn't matter if I stack phase A with phase B or phase B with phase A. What's maybe less obvious is that this operation is actually commutative as well. Sorry, associative. If I stack A with B and then C, this is isomorphic to stacking B with C and then A. And that's only true for sort of these fermionic, well, that's probably true in many special cases, but it's always true when you stack fermionic theories. Okay, the last comment to make is that there is a special theory out of the set of invertible fermionic phases, which is the nu equals 0 theory, which plays the role of the identity element. So if I stack K0 with itself, I get K0 back. So this will actually be the trivial fermionic phase. And this is one reason why fermionic phases are actually so difficult to analyze and study. The trivial phase is actually not that trivial. It's a non-trivial modular tensor category, sort of a fermionic cousin of the toric code. Any questions?
So the relation between, say, so you said these are the K nus labeled invertible fermions.
Mm-hmm.
But So when I think of invertible front, I think of like P plus IP or something.
Mhm.
Are those,
So the new odd theories are describing P plus IP superconductors. So you have to interpret. So those are all Ising modular tensor categories where you've interpreted the fermion there as the physical fermion, and the vortex or the Ising anion as a fermion parity defect.
I see. But, okay, maybe, so if I think of P plus IP, maybe this is wrong. I don't think of the defect as being.
Yeah, it's not a mobile deconfined anion. It's a defect in the spin structure. So yeah, I made this comment that there's two ways of thinking about fermionic phases. There's actually a dictionary between them as well. It's called fermion condensation, and when you do that, you find the vortex defects are immobile, and you'll also really find that they're invertible. There'll be unique ground states on any closed manifold. But somehow all of that data of the sort of intrinsically fermionic theory, the one enriched in supervector spaces and so on, is encoded in the parent theory. So everything you can say in the superpivotal theory, you should be able to say in the parent theory. And making that precise means interpreting the emergent fermion as a physical fermion. All right, good question. Any other questions? Okay. All right, so now we're at the point where we can start thinking about what does it mean to have a symmetry of our system. I'll discuss that for the bosonic systems first, and then the fermionic systems. We'll see that there are additional constraints that come up from interpreting the physical fermion, the fermion as a physical fermion. And this actually leads to a whole plethora of consequences and various kinds of new fermionic obstructions that appear. Okay, so what is a topological symmetry of our unitary modular tensor category? This is the bosonic case. Well, the very most basic level is just applying a permutation of the topological charges. So I have this map phi, which takes the MTC back to itself, and we'll map A to phi of A, which is just some other simple object in our theory. All right. So we'll first do how the symmetries act on the objects and then on the morphisms. And then there'll be several consistency conditions that they also must satisfy. All right, so that's the first example. In the fermionic setting, we're looking for invertible maps from our fermionic MTC back to itself, which leave the fermion fixed. So we're not allowed to permute that fermion with any other fermion. It's a distinguished element. It plays a special role. It does not get permuted. At the level of objects, that's the only constraint that we have. It's otherwise very similar to the bosonic setting. All right, so what's an example of a topological symmetry? I should also say, we'll see in a moment, but they have to leave all topological data of our theory unchanged. All right, so in every single fermionic theory, you have the following symmetry. If your topological charge is a quasi-particle, do nothing. If your topological charge is a vortex, fuse it with psi. Okay, so this only acts non-trivially on the vortices, and this symmetry actually plays a very special role in the classification. It ends up being related to stacking with non-trivial fermion SPTs, but we'll see that later. Any questions? Okay. All right. So
I have a question. Maybe it's looking too far ahead or something, but so like if I think about like the describing bosonic SETs in terms of G-cross tensor categories, right? So there's a difference between the theory, the ungauged version of the theory, and then the version of the theory where you gauge the G symmetry, where you would get some other UM.
Yeah.
Right. But here, the thing that I'm kind of a little bit confused about is that in a fermionic theory, like the fermion parity defects are extrinsic defects. So we could, of course, you can also gauge the fermion parity symmetry.
Mm-hmm.
But here it looks like the UMTC we're working with is actually the gauged version of the theory.
Yeah, essentially that. So if you wanted to gauge fermion parity, it just means forget about all the additional fermionic constraints that I've inputted.
Right. So the ungauged version of a fermionic theory, it just means that you have extra, you keep track of differences between vortices and quasi-particles.
Yep.
And you kind of express your, the objects, the simple objects are going to belong to one or the other.
Yep,
So
that's right.
if you gauge, you just say, forget about that.
Exactly.
Okay.
Yeah, from the MTC side, I think it's not so interesting, the fermionic story. And we even have maybe I'm being recorded, so I can't say it, but there's a belief that you can map the all the superpivotal MTCs to UMTCs via a gauging procedure. So we believe those are all equivalent. We don't know if the same statement is true for in the fermionic G-cross setting. So you can imagine we have a set of fermionic SETs that we can describe with our algebraic construction, and then one could condense the fermion to find a set of superpivotal G-cross, but we don't know if that's all of them. In the MTC setting, we believe they're all of them. Yeah, so that's one reason the SET side is actually more interesting. You get new stuff. All right, questions? Cool. Okay, so we've talked about how the symmetries act on objects. Oh, I realize I'm running out of time. We've talked about how the symmetries act on objects just by permutation. They also act on these trivalent fusion spaces, and they act in the following way. So now I'm just going to consider the fermionic symmetries. If you want to do the bosonic case, just drop the F's here. So the fusion space is mapped to another fusion space where we permuted the external lines. And then we also allow ourselves to pick up this complex number, this non-zero complex number, which we call a U symbol. And that U symbol has to satisfy a consistency condition. We should be allowed to associate and then apply the symmetry, or apply the symmetry and then associate. And there's a similar condition for the R symbol as well. Okay. All right, and then we'll say two topological symmetries are considered equivalent if they're related by a fermionic natural isomorphism, where fermionic natural isomorphism is defined as the following. So upsilon is the natural isomorphism. This is a topological symmetry. It's one that doesn't permute the objects, but it does something very trivial. It just multiplies by a complex number, one associated for each object. All right, and the additional constraint that we have to put in for fermionic theories is to require that gamma psi is always +1. Okay, and in principle, this is enough. I could end the talk here today and just say, go learn G-cross braided tensor categories and learn out the consequences of setting gamma psi to be +1. Of course, I won't do that. I'll guide you through all the consequences, but in principle, I think that's really all we've been doing. Okay. All right, so as I said, the two topological symmetries are considered equivalent if they're related by that natural isomorphism. I'll denote the equivalence classes of topological symmetries via these square brackets. From there, we get this fermionic topological symmetry group, which is the set of all fermionic topological symmetries. And it's a group where the group operation is just given by composition. And note that if we drop the brackets and just pick representatives of our fermionic topological symmetries, phi f will differ from phi f prime and phi f prime prime by a fermionic natural isomorphism. All right, so what we're really interested in is looking at fermionic systems that have on-site unitary symmetries. And we want to think about the effective theory that, that we can use to describe those on-site symmetries. So here we'll have our global symmetry group, which will be G, just a finite group. We'll have our fermion parity symmetry group. So this is associated with conservation of fermion parity in the system and related to the fact that our fermion MTC has the Z2 grading. And then the full fermionic symmetry group will be a Z2F or a Z2 extension of G determined by some 2 cocycle. And for now, that 2 cocycle will be arbitrary, but we'll see that there'll be certain obstructions that we encounter later, which sort of remove certain possibilities for that 2 cocycle. Okay. All right, so now we can do our classification either with respect to M0 or M. So on this slide, I will say we're doing it with respect to M. And the first piece of data we have to choose is a homomorphism from G into aught F of M. Now there's a very annoying subtlety that you can't actually choose a linear action on these theories as you would in every bosonic theory. You actually have to choose a projective symmetry action. And I don't want to get into it, but it's related to a special type of vortex symmetry that I mentioned earlier. So for the rest of the talk, those Qs will all be set to 0, but I just wanted to highlight it because it is something that's new in these fermionic theories. All right, so now you can ask fun questions. Like suppose that we started with a symmetry action on the super MTC, so not the full fermionic MTC, determined by this map rho 0 from G to aught F of M0. And then we can ask, does that symmetry action extend to a symmetry action on the full fermionic MTC? And so this turns out to not always be the case. There's a new obstruction you find, which is an obstruction to extending the symmetry action. And one can show, although I won't discuss it anymore, that if this obstruction doesn't vanish, then we can build a 3+1D fermion SPT, which cancels that obstruction for us. So the theory can be built consistently at the boundary of some non-trivial fermion SPT. All right.
That's surprising given that the obstruction lives in H2. Thought it should live in, well, I mean, okay, I mean, maybe that would pop out of some Vortism or supercoilology classification of fermion SPT.
Yes, so there's a beyond supercoilology classification where you have, well, if you're familiar with defect decorated domain wall constructions, your bulk 3+1D FSPT is described by G foams. And then at the, you can assign sort of lower dimensional FSPT data to the intersections of those G foams. The one-dimensional intersections take two group labels and they're, they label a Majorana chain there. So that's exactly this one.
Okay.
And then there'll be triple intersections that have an H3 of GZ2. We'll encounter that later. And then there's the usual H4. Okay. But yeah, I agree. It was surprising. It's cool though. All right. So where does this thing come from? Well, first off, we have the symmetry action rho 0 from aught F in aught F of M0. And one must first ask, is this even a restriction of a symmetry action on aught F of M? If it's not, you're done. So let's assume that that's the case. If that is the case, then we can pick an arbitrary lift of the symmetry action from aught F of M0 to aught F of M. And then we apply the standard cohomology trick where we compute a 2-co cycle in this way. So we ask, does our lifted symmetry action compose like a group homomorphism? And so that will define some element in H2. If that element vanishes, then we can find a way to modify our lifted symmetry action such that it really acts like a homomorphism. All right. Moreover, when the obstruction vanishes, there's a tensor valued in H1, which amounts to changing the symmetry action by this sort of special fermionic automorphism I mentioned a few slides ago, the one that only permutes the vortices. Any questions? All right. So the next thing we want to do is ask, how does the symmetry localize on the particles? And this goes under the name of symmetry rationalization. All right, so this is a picture I took from that seminal paper. So in the real world, in our physical system, the symmetries are realized by a product of local unitary operators, and we'll call that the full product of operators R sub G. And when we act on a system that has quasi-particles sitting around, those R sub G can be, well, first the state is symmetric everywhere. So in most of the places, they just disappear as we act on our space. Near the topological charges, they'll act like a permutation up to some unitary matrix. Unitary matrix localized at those particles. Okay, and so one can show that those sort of localized unitary matrices satisfy sort of a projective condition shown here. And the projected phases that we pick up, we call eta. Okay, so those etas relate the localized symmetry action of G and H to the localized symmetry action of GH. Okay, so now it turns out not all global symmetries of a modular tensor category can be realized physically. They can't all be realized by a product of local unitaries. And yeah, so what the authors of the paper on the previous page showed was that there's actually an obstruction, an H3 valued obstruction, which actually dates back to an older paper by adding up Algebraic and enriches, which physically tells you when it is possible to realize the symmetry action by a product of local unitary operators. And that obstruction is some invariant valued in H3 of GA. All right, and it is purely defined in terms of the natural isomorphisms that relate the symmetry action rho GH to rho G and rho H. All right, when that obstruction vanishes, then all symmetry fractalization patterns can be realized via a torsor valued in H2. Okay, so these are like, all the consistent projective symmetry actions on our particles. Any questions about this? All right. Okay, so how does this work in the fermionic setting? Well, in that setting, all we did was restrict the set of natural isomorphisms that we have. So that's okay. That means we can define the same H3 obstruction as we had before. But when you do that, you then look at the sort of torsorial classification that you had in the bosonic case, and you find that it looks a little bit funny. It's not H2 of GA, it's Z2 of G valued in all of the abelian anyons, modulo co-boundaries that are valued in the abelian quasiparticles. I apologize. I should have said curly A stands for all of the abelian objects in our modular tensor category. So those are objects of quantum dimension 1. Okay, and ultimately the reason why we're quotienting by D2 of G valued in A naught is due to this physical fermion. So the constraint that we imposed earlier, gamma psi equals +1, if you run through all the mechanics, tells you that you're only allowed a restricted set of co-boundaries when you look at this torsorial classification. All right. Any questions here? Great. So yeah, I will describe in a moment how there's actually a more natural way to think about this H3 obstruction in a fermionic setting in terms of two different kinds of H3 obstructions, which physically represent whether you can locally realize the symmetry action on the quasi-particles, and then ask whether that symmetry action extends to the vortices. Well, the localization of that symmetry action extends to a localized symmetry action on the vortices. All right. So yeah, what one finds is, when you go through this classification, you find that there are many questions you can ask, which all have the same flavor. Can we take a symmetry action on something and extend it to something else? So the game of this slide will be to ask whether there exists a symmetry action on something and does it extend to something else? Okay, so the first step is the one we just looked at. Does there exist a localization of the symmetry action? The obstruction, the corresponding obstruction lives in H3 of GA, and the torsor is shown on the right-hand side. So the next thing you can ask is, does there, whoa, I realized I deleted a slide. Okay, let me go back a moment. Oh, no, I just forgot to mention it. So torsors valued in vortices will actually change this Tuco cycle associated with our fermionic symmetry group. Okay, so that's just a fact. I didn't show you it, but believe me. Okay, So then you can ask, does there exist a localization of the symmetry action that respects the fermionic symmetry group? We call that OW. There's a formula in our paper for it, and it's valued in those two groups, depending on whether you have abelian vortices or not. Okay, and its torsor lives in the abelian quasi-particles. All right. The next question you can ask is similar to just replacing the fermion MTC with the super MTC. So you can ask, does there exist a localization of the symmetry action on the super MTC? And that obstruction lives in H3 of G A hat, where A hat is the set of abelian topological charges modulo the fermion. All right, let me skip that one. This is just the same as the previous one, except with respect to a fixed GF. And the last one is probably the most important. So it asks, does there exist a symmetry fractionalization on the quasi-particles that extends to the vortices? And so this, one can go through the mechanics and compute that obstruction, and you find that it's valued in Z2 psi. And if that obstruction is non-trivial, then there is some 3 + 1D fermion SPT that you can build, which cancels that anomaly. And as we were talking about earlier, that 3 + 1D SPT is built out of G foams, where you've decorated the triple intersection of these foams with fermions. All right, any questions here?
Yeah, so I thought from the beginning that the starting point is like you fix rather than M0.
So there's two options. You can either fix an M0 and then ask a bunch of extension questions about does it extend to M and then extend to symmetries.
So that's what these questions are about, right? So if I start with M0 and I have some group action on the M0, does it extend?
Yep. Yeah, O eta is asking whether the symmetry fractionalization on M0 extends to M1. And for us to even make sense of that question, we also need our O rho to vanish, which was asking, does our symmetry action on M0 extend to a symmetry action on M1?
That was the thing from before.
A few slides ago. Yeah, there's sort of this multi-tiered classification where you start thinking about symmetry actions and how they extend, and then symmetry fractionalizations and how they extend. And then next we do symmetry defectifications and how they extend.
So but if we think of it as just starting from the M on M0, then
many of these obstructions would be irrelevant. In fact, the only ones that would be relevant in that case are OW, I believe. Yep. OW, the second obstruction.
not the first one.
The first one is also relevant, but it's more natural to consider the classification with respect to a fixed global fermionic symmetry group. So the OW is like, those are like,
It's the GF you want outlet.
I don't know if I'd say it that way. They are the, it asks whether there is a fractionalization that can be found with the same GF that you started with, or the same GF, the GF specified by W.
I see.
Whereas the first one just, doesn't care about GF. All right. So I see I have 5 minutes left. So let me talk about these things quite quickly. So the next step of the classification is to introduce symmetry defects. And so there's sort of an analog of the unitary modular tensor category that includes G labels on all of the objects. So in particular, the tensor category will have a GF grading as shown in the top. The objects will all be GF graded as well, and we'll explicitly write down what their spin structure label is. So the first label tells you whether the object braids trivially with the fermion or non-trivially. And the second label tells you which defect sector it lives in. Okay, and the way we like to think about these is the lines or the calculus that we draw all live at terminations of G-foams. So that's what's shown on the right. And every time an object passes through a G-foam, it picks up one of these G actions. All right. So I'm running out of time, so I don't want to say too much about this. There are more consistency conditions that one has to satisfy. They're called the pentagon and heptagon equations. The pentagon equation is the same one that we encountered before. The heptagon equation is exactly like the hexagon equation, except we add G labels to all of our topological charges. And there are two steps which aren't present in the hexagon equation, which correspond to sliding vertices through G foams or sliding a G foam over a vertex. All right. And what the authors of Eddinghoff, Nikschitz, and Ostrich showed, sorry to include the reference, and also in the physics paper by Bonnerson, Barkeshli, Wang, and Meng Cheng, showed that the failure to be able to solve the pentagon and heptagon equations is encoded in an H4 obstruction, so H4 of GU1. And this O only depends on our modular tensor category, our choice of symmetry action, our U symbols, and our eta symbols. Okay, so that's all data associated just with the modular tensor category itself. When this obstruction vanishes, we have a torsorial classification by elements in H3 of GU1. And physically, one can understand those as stacking bosonic SPTs on top of our G cross braided tensor category. Any questions? No, good. Okay, so don't read this whole table. It's just meant to show you we have a table in our paper which summarizes sort of all of the classification data. First starting as we go through the columns, if we start with bosonic theory, in the middle, we start with the fermionic modular tensor category. And the last column, we start with the supermodular tensor category. And as you go through the rows, you add more and more structure, and we tabulate the various obstructions that one encounters as you go through those rows. All right, so I know it's only supposed to be 50 minutes. Can I spend 3-4 more minutes on just the right column? Okay, great, thank you. So yeah, the right column is probably the most interesting, maybe most complicated part of this classification. So in that column, we are starting with a supermodular tensor category, M0, and we fix a global fermionic symmetry group, GF. All right, and then in the first step, we pick a symmetry action, which, as I mentioned earlier, is this sort of Q projective symmetry action, which we're ignoring. That's what that phi superscript 0 means there. So we pick this homomorphism. And then we ask, does there exist a symmetry localization? So that's encoded in this obstruction. Does there exist a symmetry localization on the quasi-particles? That's O0 of W, shown there. When there does exist a symmetry localization, then we find there is a torsorial realization of all other symmetry localizations by elements in H2, where A0 is the abelian quasi-particles modulo the fermion. All right, the next step is to introduce defects. And so now we have sort of two axes to look at. We need to introduce the vortices and we need to introduce the G defects, and they have some interplay with one another. Oh yeah, so I guess the first, yeah, so the first question is, which fermionic modular tensor category are we considering? So we know there'll be 16 choices. We pick one. Then we ask, does the symmetry on the quasi-particles extend to the vortices? That's O rho. Oh, maybe I have, yeah, that's O rho. The next one is, if the symmetry extends from quasi-particles to vortices, does the symmetry fractionalization that we picked in this step extend from the quasi-particles to vortices? That's O eta. And then lastly, we have the defectification obstruction, which is the one from the previous slide. And that's the same as the bosonic case. All right. Now, when we have our successful G-cross braided tensor category of this fermionic theory, there are still a torsorial classification of that. So in the bosonic setting, the torsorial classification of the defectifications is just given by SPT stacking. In the fermionic setting, there are two torsorial classifications you can consider. One is fermion SPT stacking. We call that group G321 because it depends on a 3, 2, and 1 cochain. And what this fermion SPT stacking will do is change the symmetry action of the symmetry action on the vortices by this vortex permuting symmetry action. It will change the symmetry fractionalization on the quasiparticles and vortices by some Z2 psi value cochain, and then it can also just glue in bosonic SPTs with it. The Z16 torsor is the set of invertible fermionic orders which have a GF crossed extension. So it's a subset of Z16. Those theories can be stacked with our GF extensions and then condense the fermions. And yeah, so that will cycle us through the sort of set of allowed Z16 section. That will cycle us through the allowed sort of Z6, the allowed Z2F extensions of our super MTC. And then those two groups, the Z16 group and the G321 group can be combined into a larger group, and the sort of extension class and how they can combine can be computed explicitly through condensation. All right, and since I'm over time, I will skip a few topics and just say thank you for your attention. Yes, this, I presented this classification of fermionic MTCs where we consider this sort of long extension problem where we think about how we extend symmetry actions from subcategories to larger parts of the categories and eventually introduce defects.
Yeah, thank you very much, David, for the very nice talk. Are there questions? So also from the audience outside and obviously from here as well. Yeah, Marvin.
So there was a torsor for symmetry localization, there's a H2.
Mm-hmm.
Does that correspond to decorating of the fermion strings with
Yes, roughly. But that intuitive picture is hard to make precise when you have non-trivial symmetry actions. But yes, I think you're right, and that's something we should talk about later.
Further questions, then please ask them aloud, because otherwise it's not, one cannot hear it on the audio. Further questions? From outside, anybody from? Okay, then if that's not the case, let's thank the speaker again. Well, and next week, I think Howie will continue his series of talks on quantum information theory. Thank you.